No, because I realized after I started it the last time, I went, oh, dummy me. I just needed to do this and you're fine. So that's a regular.
And I need my training under thing too.
That's his job.
What do we got? Oh, yeah.
Oh, he's been running. Okay.
That should work. Okay.
Yeah, so is it still in the water? Just not in the water bath?
Okay. Bill, this should just be quick arrows. Should be on. Back and forth.
Okay, no, I'll take care of that.
There you go.
No, I got it.
Yeah,
Thanks for doing that. I mean, today's my day.
Gives you a short.
No,
No, give it a few more minutes and yeah. Bill,
I
real
know.
short, just give your name, where you're from, thank you again for speaking, and
Yeah.
Ones that never got shot.
Yeah. So we had
our infantry stuff. We were getting signal that's like a weird signal. Little cottonwood tree. Owl nest. Like you're saying, 6 radio towers.
So yeah, but if we got it, there's
The owls were, you put them out, the owls.
because I got
Yeah.
Like I could hook up my computer up and have like a just put it up like giant and I could
Thank you for taking the
But yeah, do you want to pursue
That's it. So we're gonna start our speaker portion of the meeting. So I'd like to introduce everybody. Bill Mooney. Bill is with chemistry and industrial. So,
Yeah, I printed out this, that's on the table for everybody to see. Just to take it has the bio descriptor of what we're talking about today, so if you're interested in that, grab one. I just wanted to say, I'm sorry.
that's okay, Scott. So we have and once again, I'd like to thank Bill. No. Denise is, I should say, we had some issues with speakers we had lined up. How they say Scott was it 2 hours?
2.5 years.
You were looking at the. So, Bill and Denise, thankfully, graciously stepped up and helped us. We appreciate that. Now, without further ado.
Thank you. Okay. I don't know that I really need this, but we're recording it or something.
You had that one launching, what?
Not really this one, but we are checking her because I've got them out and we sent them the link, so we'll see if anybody takes them. We're supposed to have 3 people, so.
Don't break it.
Well, that's good. I just got rid of this.
Maybe you should.
This always reminds me when I was up at CSU doing some graduate work. First day of class, Dr. Blem notices that in undergraduate school, everyone sits in the back classes, but in grad school, everybody sits at the front. They're fighting for the front seat. I would take the front seat because I can't see or can't hear at my age anymore, but so maybe we're just regressing. So, as I told you earlier, primarily what I do is engineering controls, and most of that has to do with some kind of a fan or blower system, and I suspect that most of you in here work with or around fan or blower systems. Anyone not? You would fan, blower, whatever. Okay, so this class was originally designed. This presentation was really designed for that have to go out and sometimes troubleshoot, and they'll evaluate the system and find that it's not too much overexposure or over or something, and they might find out what they can do to fix it and make it work better, or what the problem is. And so oftentimes it happens to be the ventilation system. And in industrial hierarchy, when we're dealing with oxidized protocols, the first thing we always want to do is just get rid of the offending material, substitution, and then elimination, and then work on down through the hierarchy. Engineering controls is always, one of the upper echelons, like in the middle of the pack, and then from there we go to administrative controls, and then finally go to PE. So if you want to keep people out of respiratory, those are the last resort. So you want to design some engineering control to keep your folks safe, and then OSHA likes to see the engineering control as one of the first things. So today we're going to talk about a bunch of things. Now this talk is designed for a little format. So I'm going to I'll present these topics, but I'm going to skim over a lot. So you can put your calculators away because we're not going to be doing a whole lot of stuff with fan laws. And we'll just briefly discuss fan curves. So just very briefly.
Do we have to take a quiz?
Right now. And so then hopefully I'll spend most of the time on the troubleshooting aspects of these different hand type systems. So In industrial heating applications, and a lot of infrastructure, we have the two styles of controls, and there's the general or dilution exhaust ventilation, and then there's the local exhaust ventilation. So general dilution might be large spaces, a big industrial warehouse space or a fabrication facility or something. We got a lot of air movement in the facility, and we're using large fans to accomplish just a general dilution of what's going on in the space. Local exhaust ventilation is what you typically see, where we have a dedicated fan, often one fan per device or hood, like in a biosafety cabinet or a fume hood, maybe a receiving hood. And then we see a lot more of the multiple hoods on a dedicated lab exhaust with various flow control valves and inquiries or blade dampers, but there's different ways of controlling the flow so that you have one fan that does a whole bunch of different stuff. This is my new bathroom fan. I'm going back here next month. This is I guess a general dilution, generally ventilation, happens to be for a mine. That's me, and it's really loud here, really loud. And we'll go through some of these different types of fans. This happens to be a vane axial fan, and it has what we call guide vanes or inlet vanes on the inlet of the fan. I'll show you what those are all about. Yeah, so okay, so local exhaust ventilation. Local exhaust would be, a typical kind of receiving hood where you have some grinding application or something, it's throwing material off and you throw it into there. Or a slot hood over an industrial process or a production process like this. We're generating dust inside this device. It's a scoring device that scores calcium acetate insulation materials that generate a lot of dust. So an enclosure system with a slot hood here and a canopy hood over here. And then, a lot of you guys are involved with a lab exhaust. So maybe your typical fume hood or your biosafety cabinet, as Ed was talking about earlier. Aseptic isolators, which serves a similar purpose. Glove boxes, we used to call them. And these are all local exhaust ventilation applications. So when it comes to these different types of fan systems, realistically, you're going to see two styles of fans. And this first one is called a centrifugal fan, and it uses a fan wheel and a motor that drives the wheel. And there's basically three styles of wheels, and there's some variances on these too. So like on a radial blade, there's radial tip blades, there's shrouded radial blades, there's paddle type or open blades, it's different, but it's a basic radial blade. And radial blade fans have certain characteristics, the way they perform. And then there's the backward inclined blades, and then there's the forward curve, we call these cases. And you might typically see them in smaller systems that don't require a whole lot of pressure characteristics. More airflow oriented versus oriented. Centrifugal fans bring air in from the inlet side of the fan, and it's discharged 90 degrees. So the air comes in one axis, and then it leaves at a second axis. And that defines a centrifugal fan. So here's a typical fume hood where we have a canopy, it's not a canopy connection, it's just a direct connection, as Ed was talking about earlier, up into the inlet of the centrifugal fan, and then it discharges. So it comes in this way, and it discharges in a different plane. High pressure centrifugals typically are going to take the form of radial blade applications. And you might see them that look sort of like this. They're round, maybe a fiberglass or fiberglass plastic, aluminum housings, steel housings. And they're characterized by a blade that's shaped like a spoke on a bicycle or a wheel of some kind, that the spoke radiates directly out from the center portion of the fan. These are particularly suitable for material handling and for high pressure applications. This fan is probably not in the right order of this picture, but this is an inline centrifugal fan. So in this case, the air, it's a centrifugal fan, the air is coming in and is exiting in the same plane. But technically, no, because the air enters the fan wheel here and is thrown out at 90 degrees from the fan wheel. And then the pressure inside the cabinet redirects the air along the same axis as the propeller. So it's technically a centrifugal fan, but it acts like an axial flow fan. This is another case of some centrifugal type fans. These are called unhoused fans. You see a lot in the mechanical devices. This happens to be a wet scrubber. So you can have a welding application where you're welding stuff on this vacuum down in, and there's a water reservoir down here, and the fan is in this section over here, and it's an unhoused wheel, so it doesn't direct the air straight in an opposite plane, and it's still a centrifugal fan. And I apologize, there's a couple of slides missing, but it's not that critical. They talk about the radial, we talk about the radial paddle type blade, and the forward curve, the backward curve, centrifugals, and I had that little picture up front. I thought I had one that was more detailed on it, but maybe not, it may pop up here. So axial fans, the air enters from one direction and it moves along the central axis of the fan and moves straight out the back. And so this one is called a tube axial fan. This is a similar arrangement, except it's a vane axial fan because it's guide vanes behind it. When air comes out of the tube axial fan, and the fan is spinning, the air comes spinning as it comes out and moving down the top. The guide vanes behind it stringing that air out allows you to develop pressure and more efficiency on the fan. And this is what they look like on the side of the plane, a plan view. I mean, air enters this way and enters the hub and the blade assembly here, it goes straight out the back. And here's the one that has the vanes in the back to eliminate the swirl on the fan. There's another axial type fan, a panel fan, a prop fan, a wall fan, and these would be typically used for large space ventilation, like we were talking about earlier. Characteristic of this type of fan, though, is high volume, very low pressure. Doesn't develop any static capability. You take the same fan and you put it in a tube, you can develop some more static pressure, but there's still low static applications. Everyone know what static pressure means? Anyone know what static pressure means? Okay, so real quick, static pressure is the pressure that's developed by a moving air, a moving fluid that's exerted in all directions. So when you pressurize this tube, the static pressure is moving this way, it's moving backwards. The whole cavity develops a pressure, and that's static pressure. And that's as opposed to velocity pressure. Velocity pressure is air pressure that's a vector is generated in a specific direction. Velocity pressure is always positive. There's no negative velocity pressure. Even if it's going backwards, it's developing a positive pressure in the opposite direction. Static pressure can be positive or negative, and we use this when we're designing fan systems. And I'll talk about that briefly when we get to that section. Here's some more applications for roof ventilators. This is an axial roof ventilator. Here's a centrifugal roof ventilator. Here's a high capacity one. It's got guide vanes on the inlet. and it's got blades inside here. This one might be 55,000 CFM. This one might be 55 CFM, or 500 or 300 CFM. Okay, so I talked about the static pressure. There's three characteristics that we're going to look at when we put fan systems together. One, the first one, and typically the primary one, is the CFM. How much air do we have to move? How much air do we need? That might be industrial high-heat application. We have to develop a certain approach velocity to the fan and capture the contaminant that we generate. So you got a welder who's sitting there like this stuff, and you want to put a little fluid here, pull it in there away from the space, and you need to get a certain velocity to get that air up into the hood so that it doesn't knock into the space. So the approach velocity of the air determines how much CFM you need. The pressure is what's developed as we move that air out of the breathing zone where it's going through some type of a system, duct system, or out through the roof, or in the case of a wall fan is very low pressure. It still has to move. It still has to be a difference in pressure for air to move. Air moves on different pressures. So you can create a suction or a negative pressure on one side, and a positive pressure on the other. That's what's causing air to move. And then the third thing that we want to consider is the brake horsepower. How much power is it taking to move air? And that is to take your CFM, put it under some load, some pressure load, and drive it with some motive force, typically an electric motor. All of these three items can be related to the revolutions per minute, the speed at which the fan is turning. And that's the critical issue with virtually every kind of fan. How fast do you sustain it? I'm going to show you some examples of this. So when we look at a fan, as a designer, I'm going to need what was this well do here? I need 100 feet a minute to get away from this space. The duct is 8 inches in diameter, and you take the cross-sectional area times the velocity, you come up with the CFM that you need to do that. Then you need to determine how much duct is there going to be, how much flex duct, how much pressure drop across the fan, and how much discharge duct pressure does it take to get that air out of there. So we have to define the pressure, and we can look up tables or calculate these different pressures and come up with the requirement. We have the CFM we know, and we have the pressure. And that defines our system curve. And I'm going to show you that in a minute. So these two curves are pressure curves. This is the static pressure. This is the total pressure. You can size a fan or apply a fan based on either one. The appropriate way to do it is with total pressure, but almost nobody does that. Even the fan manufacturers give you their fans in terms of static pressure. There's a little misnomer in that, but this course is not an engineering class, so I'm not going to go into that now. This is the efficiency curve, which we haven't talked about at all, but any fan, when you select a fan, and it's going to be moving at such and such an RPM, it's moving so much air, so much CFM, you want to select the fan that along an appropriate section of its efficiency curve so that you get the most bang for your power buck. And so if you took this fan and you want to move, say, 10,000 CFM, you look at this efficiency curve, it's way down here if you look at the total efficiency. If you look at the static efficiency curve, it'd be way down here as you select it. You want to select the fan somewhere along the peak portion of its efficiency curve. And then that equates to horsepower. Horsepower curves for fans can be continuing a power curve for a fan. When it starts out at zero pressure or 0 RPM, and RPM continues to rise, the horsepower continues to go up, and the fan uses more and more horsepower as you move more and more air. Other fans are non-overloading, so they have a kind of a hyperbolic shape to those fan curves. So again, it's not something we're going to spend a whole lot of time on, but everyone's heard of the fan laws, right? No, okay, so when you select the fan, the first thing we talked about was how much air are we gonna move in that fan? And so we'll look at the fan curve and we'll say, okay, we need 5,000 CFM. We look at that, we take the CFM that we need on the curve and we develop how fast the fan has to turn in order to develop that. Now, if you add more pressure, you're gonna have to turn the fan a little bit faster. Everything relates back to RPM. So the CFM and the RPM are directly related. I have a better version of this formula, but they're directly related. So as you double the RPM on a fan, you double the CFM. Pure and simple. 2 times as fast, 2 times as much air. Half as fast, half as much air. Very simple, direct ratio. Oops. The static pressure on the fan, though, which is the second design characteristic that we want to look at on our system, the static pressure is going to change by the RPM too, but it rises to the square of the RPM. So this throws a different wrinkle. It's just double the speed of the thing and expect the pressure to double. The pressure is going to go up 4 times if you double the speed, because it's a quadratic or square function. And here's the real rub. The power changes by the cube of the RPM on the fan. So a lot of places I go into, and we say, it's just not getting it. You get a little bit more air. So double the amount of air would be great. But when you double the amount of air, you increase the horsepower by 8 times. So it's 2 times 2 is 4 times 2 is 8. So doubling the RPM to double the CFM is going to increase your horsepower 8 times, 800% increase.
Hey, Bill?
Yes.
So let's say you could do it, or let's say in design, you went ahead and did that, you retrofitted for that, right? But it also is important, it's significant to the amount of space that fan's taken care of, because now all of a sudden, if you doubled the amount of fan, wouldn't you create a vacuum or a pressurization that's...
Conceivably, if it's a ducted fan, yeah, you're going to change the static pressure. You have more static on the suction side and more negative static on the suction side, more positive static on it. Or if it's a fan in a given space. But that's a different equation altogether, because now we're talking about makeup air to a space. So if you're going to double the amount of air that you need in a space, you have to double the makeup air to maintain the same room pressure. It's not really a fan function. Yes.
Yeah, Bill, if you're gonna run the horsepower from 2 to 8,
Yeah.
double the CFM. Your operating cost load is it's not you got double the air, now you got double the cost. Maybe go even more than that.
Oh yeah, and not only that, but you're going to move that fan way out of its peak efficiency range too, if it's been properly selected in the first place. That probably hasn't been properly selected, but a lot of times when I go into jobs and there's people that are kind of uninitiated, and I'll go into a job and they change the speed on the fan because they need to get more air, but they don't realize that they increase the horsepower. They might be overloading that motor, and next thing you know, you got a burnout motor because you overloaded the motor without realizing that a little increase in that speed is a lot of increase in horsepower ahead.
Yeah, Bill, you'd be surprised how little attention is paid to this. A lot of cases, so-called experts putting in exhaust fans in my business to ventilate a hood.
Sure.
The hood manufacturer says, okay, this hood exhausts 300 CFM there. So the building engineer goes to Granger catalog. Oh yeah, there's one that's 300 CFM. He puts it up 4 stories above the hood. And then I come in and say, well, this thing's not working. Well, look at here. It says 300 CFM right in the Granger catalog.
Yeah,
You don't even pay attention to any of
he
it.
didn't look at the static,
No.
static capability of fans. You got to look at that fan curve to determine where you want to be on that.
By the way, if all of you are following everything Bill's been saying, you can have a job with me, because we for engineers. I'm barely hanging on with you.
Okay, so this discussion isn't to teach you how to design fan systems. All I want you to do is to be able to recognize when you walk into a place, or if somebody may be talking about doing something, get the wheels going, you know? I don't know that you can do that, because if you have to, and I always talk, I'm really good friends with Cynthia Elwood, and we worked together for years on ventilation projects and enclosures, and I always joke with her about, you know, the system isn't working, we'll throw some more horsepower at it. If you have PM, you're gonna be beyond the horsepower characteristic or capability of that motor, I mean, the motor increase. But then there's a lot of other things that go into that, what happens when you start changing that stuff around. So, the thing I want you to take away from this is that cube function on the horsepower requirement. And here it is graphically. So if you take a fan that's running at, say, 1 inch of static pressure and 1,000 CFM, you say, oh, I'll double the CFM on that fan. You can go from 0 static here to 1,000 CFM here to 2,000 CFM. So that's the RPM curve, direct ratio, right? The static pressure curve rises to the cube, to the square, so you double that CFM, the static pressure is going to go 4 times up. But look what happens to the horsepower. Here's that curve. So the more you increase that speed, you can get horsepower curves going up 2,000, 3,000% by saying, I want to get, 25,000 CFM out of a 10,000 CFM fan. It's not the way to do it. There's some other ways, and I'll talk briefly about it if we get to that. So we take our fan curve. So this is an RPM curve for a fan, a typical fan. So this might be, say, 1,000 RPM. When you design a system, you say, I'm going to have this much duct, I'm going to have this many elbows, I'm going to have a hood entry loss on my biosafety cabinet, or on my, not a biosafety cabinet, because it's not direct coupled, but on a fume hood. I got entry losses here, I've got suction side duct work, I got discharge duct work, I got so much static pressure. And you might select the fan at this point over here, or maybe you select it at this point here. Most fans have some region over here. They say, don't pick your fan in this range. It's not going to be effective for you. And many fans have an unstable region in that fan. If you put too much pressure on it, put too much resistance on the system, you're going to be into unstable or the surge region of the fan. Centrifugal, forward curve centrifugals have a really weird surge region in those fans. The curves actually look like this. So you take your system, this is a system curve, you say, oh, I added up all my system, and if I'm moving 2,000 CFM, it's going to be, say this is 2,000 right here, it's going to be at 4 inches of static pressure. You take your system curve and you overlap it onto the performance curve. So you take this curve here, for instance, and you overlap it onto here, and that's how you make your fan selection. So, and then you can change that. You can say, if I can take 10 elbows out of this system or reduce the duct by 150 feet, I can get that static pressure to go from this point over here down to this point here. You're going to create a new system curve, and you're going to be able to get along the same RPM of that fan, you're going to get this much more air from this point here to this point here. And so that's a better way to increase the capacity, reduce the pressure or the resistance on the system. So here's another way of writing these curves. It's just ratios. Horsepower 1, that's the original condition, divided by horsepower 2 is what the new horsepower would be, is related to the RPM by the cube. Horsepower varies to the cube of the RPM. That's the takeaway from this whole thing. So how do you increase or reduce the capacity of a fan? There's a number of ways of doing this, and some are more efficient. That big axial flow that I showed you in that mine shaft, that blade was 15 feet in diameter, right? That's the size of that fan. it had inlet vanes on it. And the inlet vane looks like a damper. When the damper blades are flat, it chokes off the air into the fan. When the damper blades are wide open, the air goes straight into the fan. But when you modulate those blades, you change the pitch or the angle on the blade. It doesn't work like a damper. What it does is it imparts swirl to that air. And you want to impart the swirl in the direction that the fan wheel is spinning. If you impart the swirl into the direction of the air of the fan, you reduce the efficiency of the fan, you drop the static pressure, and you deliver less air. So you can modulate a fan by putting inlet vanes on it and inducing swirl on the inlet side of the fan. We're going to talk about system effects in a few minutes, and that's all about what happens when air swirls or air enters a fan improperly. But this is also a means of controlling capacity on a fan. I was in the Denver Art Museum years ago, and they had a giant centrifugal train fan on there, and it had inlet vanes to modulate the capacity of the fan. When the building was cool enough, they needed less air, they had VAV boxes in the building, and they put a set of inlet vanes. They put the vanes in backwards. And so it was imparting the swirl in the opposite direction instead of the rotation of the fan. And this fan had been there, I bet you it's been there for 40 years, before the new remodel of the Art Museum. And so what are they doing? Yeah, they're reducing the capacity. The horsepower is going way up now. They did exactly the opposite. So, and I don't know that they ever changed it, but they remodeled the Art Museum. Another way on propeller type fans is to change the pitch or the angle of the blade. And this gives you real good capacity control. It's like everyone here's flown on some turboprop airplane, and you look out the window and those things are going like crazy and the plane's not moving. That's because the blades are flat. They're just chopping straight through the air. And then when they want to start moving, they change the pitch on the blade, so the blade goes from this to this to this. And the more pitch they put on it, the more air it moves, the greater vacuum it creates in front of and that pulls the plane forward. So airplanes do it. They move air by changing the pitch on it. We see these a lot on like cooling towers, and certain types of large axial flow fans have variable pitch control on them too. This is a graph of some different methods of controlling fan capacity. And so this A curve is the inlet vane control, and that's this curve here. So you can reduce your power to about 50% by changing the swirl on the inlet vane over here. And then of course it goes up to 100% at that point. And then you go into like a variable pitch. That's very effective, but there aren't that many fans that use a variable pitch. So you go almost down to 0 with a variable pitch. An ideal fan curve or capacity curve would look like this. This is the one that we're seeing almost universally anymore. Variable speed control. These can go on axial flows or centrifugal fans, and this electronic device that takes the AC electrical signal that's going to a fan, rectifies it to DC, changes the frequency of it, and by converting it back to AC, changes the frequency on the system, and the frequency and the number of poles on a motor are what determines the motor speed, right? So you change the speed by changing the voltage input or the frequency of the voltage, and you get a really good C curve, really good flat and directly proportional capacity control curve for that fan. And that's what we see everywhere. I remember when variable speed controls first came out, and I was there when they built the very first fan ever. But when the variable speed controls came out back in the maybe late 70s, you'd go into a fan room and they'd have a variable speed controller, and it's on the wall, and it's like this big giant cabinet. It sticks out this far from the wall. You go into that same room now, the variable speed controller is like the size of a toaster. And the price is a tenth of what they used to be. So we see them almost everywhere now. Okay, so now into the troubleshooting part. So we looked about some of the basics of fans and how they work and how they move and all that stuff. So you get called, or I get called on a job, and the first thing you hear about is, it's not moving enough air. Insufficient airflow. So there's a couple of things that can create insufficient airflow. Fan consideration. The fan's spinning too slow for some reason. Maybe it was designed that way. Maybe the pulleys have changed. Someone changed the shivs on the fan and changed the drive mechanism. On three-phase fans, if they ever have to change any wiring or anything on it, they put the wires back on. If they reverse any of the two wires, it's going to make the fan spin backwards. I've seen that. I can't tell you how many times I've seen that. Fan spinning backwards. Still moves air, makes a lot of noise, hums, because it doesn't know the words. And it used a lot of horsepower. And they said, gee, I don't know, it was working great the other day. Well, what's changed? Well, we had to change a overload heater in the motor controller, and they put the lines back on, the flip-flop to them. Loose or broken belts, I got a good picture of this for you. Improper clearances, so the fan, it's got, that wheel is sitting in that housing, and there's a ring that air enters that side of that fan. And if that fan is not lined up right with the ring, if it's off a little bit this way or that way, or if it's too close on one side and too far on the other side, you're gonna lose capacity on the system. If somebody changed the fan wheel and they didn't properly set the wheel again. Improper clearances, dust-loaded impellers or corrosion of the impeller or the wheel. And we see this a lot. I see it a lot. I used to see it a lot in the air filter business, which is what I did in one of my previous lives. I tell people I paid my debt to society by serving time in the air filter business. Sorry, Mike.
Yeah, I'm not sure what that means. We'll have to have a
Thank you for your
separate.
service, Mike.
Speaking of air filters, dirty clogged filters, improperly sized, improperly rated filters, those change the system curve. Remember that one that we showed with the lines going up? If you put more pressure on the system, the curve shifts a little bit to the left, and you ride up the RPM curve, and you drop down on the x-axis on the CFM curve. You lose fan capacity in that. Excessive noise is another problem that you occasionally see, not too much. It's usually an impeller issue or drives, the belts, the shifts, sometimes with a backward rotation. Shafts or bearings and shafts or obstructions in the system can cause excessive noise. I don't see too much of that, to be honest with you. I'm usually called in when they don't have enough capacity. Something's going on and we got overexposures now. Excessive airflow, too much air. Yeah, right. I don't think I've ever been called in with a job with, our system's just so damn good, we got too much air. But, maybe the fan speed's too high, improper blade pitch, oversized fan, never. Resistance too low. So, I've seen this. They're not getting enough air, they take the filters out altogether. Now they get plenty of air. Oversized ducts. There can be problems with oversizing ducts, but we don't have time to talk about that. And then the last thing we see is, and you see this more often than anything except this one, fan motor failure. Again, some of the same things, backward rotation, low system static. If you've got an overloading fan, you got a fan that has a horsepower curve that continues to rise like that one that we saw, you can overload the fan. Fluid density too high. So I've got systems that I've designed where the fan starts up at ambient temperature. It might be on an oven or something. And so you got high density air, but the fan was designed for the oven operating temperature of 350 degrees. So you just changed the whole characteristic of the fan, the pressure and the capacity of the fan in terms of its mass flow. And so you can run into big time trouble with that. Also, I designed some systems for years ago for up in the mountains where, I just did a job up at 11,000 feet. We had the whole building, we redid the whole building. And some of the systems were, the systems are all designed for 11,000 feet, which means that you use a lot less horsepower at 11,000 feet because the air isn't as dense. But if you were to take that system and move it somewhere else, down to Denver, for instance, and leave the same drives and everything on it, you're gonna overload the fan. Fluid density, long voltage. Oftentimes you'll see, these are pretty much startup issues. You don't have long voltage occur, 15 years after the fan was installed, typically. Seized bearings, though, you do see motors too small. Yeah, somebody's decided they need to get more air, they speed it up. Improperly sized overload heaters. I always say, my father used to tell me this when a troubleshooting system. I call him up, say, I'm a punk kid, I'm 24 years old and servicing system somewhere. Dad, I got this thing. My father's in the industry all his life. Did you check to see if it's plugged in? And I tell you what, it goes a little bit beyond plugged in, but tripped circuit breakers or, you open up a disconnect, there's a wire that's burnt, there's no voltage in the system. So make sure you got power in there. One of the first things you want to look at, especially if they say, well, what kind of noise does it make? It's not making any noise at all. Well, good chance it's not powered up. Okay. So I say, in troubleshooting a system, and anybody in this room can just take a look. I've been out on, I can't tell you how many jobs. I'll go into a fan room in a big building, and we'll walk into the filter bank or into the fan section of the plenum and see something that the engineer that goes in with me goes, oh, shit, I should have looked at that. And there's something really obvious. So take a look first. You don't need any tools to get your eyes on. Just take a look. So improperly aligned and tightened V-belts. This is more common than you might see. Again, fan rotation. Check the wheel and inlet cone alignment and clearances. Clean airstream surfaces. Make sure that the surfaces are clean and not causing undue restrictions. Check for clogged filters, coils, ducts. Eliminate leaks in the system. How many times you go into a system and there's a big hole in the duct somewhere downstream, nobody ever noticed it. Or another one that you see in like commercial buildings is a flex duct or two blew off the main trunk line. It's just blowing wild up into the plenum there, and the guys downstream aren't getting in the air. So just take a look. That's the whole the takeaway from this thing. System effect. We're going to talk about this. This is a critical issue. So system effect is a decrement in fan performance based upon how the fan is hooked up to the system, how it's physically connected, how the ductwork goes into the fan, how the ductwork comes out of the fan. When fans are tested in an AMPCA test lab, they're tested under ideal conditions, usually with no inlet duct at all. It's just plain free air in and some kind of a discharge duct arrangement. And these are ideal conditions for a fan. But whenever you put ductwork onto a fan, you impart unreal conditions to the fan. And there's right ways and wrong ways of doing this. And these are called system effect factors. System effects will cause a deficient fan performance. Oftentimes you can't measure it. You can't just go up to put your gauge or your magnehelic, your manometer on the system and say, this thing's supposed to be running 4.5 inches of suction static, but I'm only getting 2. You can have a system effect factor. It's still reading 4.5, but it's acting like you're only getting 2. And that's the problem with system effect. It's hard to measure, often unmeasurable. But it can be calculated or predicted, and here's the way it works. So you go into a fan system and you say, we're supposed to be moving this much air right here. This is our curve, our RPM curve. This is where the pressure that we're supposed to be operating at, and this is the selection where the system design intersects the RPM curve. That's how we selected our fan. But you know what, doggone it, I'm only getting this much air out of the system. So it's acting like there's this much more static pressure on the system, or total pressure on the system. So we generated what we call a ghost or a phantom system curve. And it has nothing to do with how much duct is on there, how much filters we have in there. It has to do with the way the fan is connected. So this would be a decrease in performance due to system effects. So let's look at some system effects. On a centrifugal fan, this is the blast area of the fan. That's this section in here down to the cutoff on the fan over here. And when air is coming out, you can see this is an expanding volume on this fan here. So air is brought in the side and it expands as it's spinning in this direction. The cavity is increasing and you have very high velocity at the tip over here and lower velocity over here. And it takes a distance downstream of the fan to get that velocity profile to smooth out, to become the ideal velocity profile in the system. And this is what we call 100% effective duct length. Anything that you connect to this fan, if you put it in this system, you're going to decrease the performance of that fan by some increment. And this chart, you don't have to know this or be able to refer to it, but this chart tells you, given a certain blast area over the outlet area, so this is the blast area here, and this is the outlet area here. Blast area divided by the outlet area defines the full profile of the fan discharge. And if you put stuff in this first section, in other words, no duct, you put an elbow or something right here, you got 0, you develop these, depending upon that blast area ratio, you develop a letter deficiency, and you have to look this up on the chart. And same with 12%. 25%, 50%, 100% effective duct length, now you can do whatever you want with it, okay? I'm gonna show you some more. There's another system, fan discharge system effect. So the air is coming in this way. If you come right off this fan and put an elbow right here, you're gonna develop a system effect based upon position A. That would be this one here, for this blast area ratio, or this one here. That's a RS. Decrease, which you have looked up in the table. Here's a bad one. When you come out of a fan that's spinning air in this direction, come out this way, and then you turn the air up in this direction. You're reversing the flow of this. It wants to come out and do this, but you're making it come out and do this. That's a real bad system effect factor for any kind of centrifugal fan. And the same with elbows going this side or that side if there's only a single inlet. They all change the system effect. We have system effects on the fan inlet too. So this is the inlet of the fan, and here's a system effect with a square elbow or a mitered elbow. Very bad system effect. Here's a elbow that's got a certain amount of duct length, and it's a radius elbow, but it's a real short radius. So we can develop a ratio between the diameter and the radius, and that we looked that up in here. 3 times the diameter. Most commercial fan systems are designed for 1.5 times the centerline radius on an elbow for a fan system. So these are more inlet systems. And so what you do is you take these numbers, these letters that you picked up from the different defects on the fan, and you look up the letter on this chart here. You compare it to the amount of airflow or the velocity of the system, and you follow it across. So suppose you got an S system, let's make one, an S system effect, and you got 20,000 CFM, you follow this curve down, or velocity, 20,000 feet per minute, and you look at it over here, and then you follow it across. It's the equivalent of adding 0.2 of an inch of additional static pressure to your system. That's as far as I'm going to go with this. Did you know? I just want you to understand how this all works. So design defects include excessive duct lengths, excessive use of flex ducts. This is a big one, excessive use of flex ducts. Poor hood design, no flanges, and inlet losses on the hood, narrow slots. These are all different types of design defects that you might bump into if you're troubleshooting a system. Here's some more on system effect. These are good and bad duct arrangements. You don't ever want to come off a duct with a straight fitting here and a 90-degree. You've got a big pressure loss in this thing over here. Here's another version of that. It's a similar size ducts on this one. You don't ever want to come with opposing duct sections coming out of a transitional figure. So you got airflow that's pulling air this way in an exhaust system. You bring an inlet here and an inlet here, and they create all this turbulence and pressure loss in this system. Here's a blank pressure reducer, pressure increaser, duct increaser. These are nice tapered fittings. These are the appropriate way to enter fittings. Appropriate ways to split fittings. 30-degree angle over here, diverging. So these are all more system effects. So we want to increase the performance of our fan. The first thing we want to consider is increasing the fan speed. It's the simplest way, but you always have to be careful about the horsepower and the maximum safe speed. I've actually seen centrifugal type fans where they increased it so much that the fan wheel blew apart. You got all over the inlet housing. Fan classification speaks to the tip speed of the fan. So that's how the outside of the fan, how fast that's moving in feet per minute. So to increase performance, you might increase the fan speed, but be very careful about horsepower and fan classification. You might add or replace fan equipment. It may be less costly than increasing the speed, because when you increase the speed of a fan, your horsepower goes up, you're paying for that every day. But you can do other things, like put in a larger fan, operate the fan at a higher CFM, higher efficiency range, and you don't have to continue to pay for that horsepower continuously. Add another fan in series. If you have to increase pressure, when you put one fan feeding into a second fan, you get the same amount of airflow as you had in the original system, but you increase the pressure. So maybe you don't have enough pressure to move the air through the system. The other side of that is, if you need to get more airflow, but you don't have to increase any pressure, add a second fan in parallel. Two fans side by side, increases the volume, maintains the pressure. Two fans in series, maintain the volume, but increase the pressure. We dead in the water?
What do you?
Nothing.
Did you die?
We're dead.
You go up there, suggest that you take a 5-minute break.
Most of the rest of this talk is pictures about stuff. And they say pictures worth 1,000 words. So I got about 30 pictures. So I got about 30,000 words to go.
Actually, we have a question. Actually, this is actually extremely interesting. I really love it, especially the fluid dynamics and there's that prior to the summer, it was the last summer I learned how to fly. And so a lot of this makes sense. And so with that being said, now I understand in an oven, if you're using a pizza oven and your motor is designed for 80 degrees Fahrenheit, but you're going up to 350 degrees Fahrenheit, and that's going to decrease your density, and that's going to increase your RPM. And I understand that's a lot of, and that's just what I'm doing.
Doesn't change the
Well, it
RPM.
doesn't, so it won't create any more pressure.
RPM is the same. Volume is the same.
So,
You go from 80 degrees to 350 degrees. The air volume is the same.
okay, so how
The
would you?
mass flow changes.
And that's,
Now you're dealing with a lot less mass. So what happens to the horsepower? RPM is staying the same, mass flow is decreased. What happens to your horsepower? Horsepower goes way down.
yeah,
So a higher temperature airstream or a lighter density airstream results in lower horsepower.
so
The
how,
converse is also true. If you've got an oven that you designed for 350 degrees, but it starts up at 80 degrees, you might be overloading that fan when it first starts up, because that air is so much denser on the start.
Okay, so it's safer in this respect if you go up to, or you go increase the temperature. So basically what I was coming to a point was so if our air system went down in the building, not the ventilation system, but the air cooler. So if the temperature increased, our fans and our hoods should stay fine, right?
If the temperature increases, yeah, your fans are gonna be fine.
Okay.
Your flow through your hood, your face velocity, everything's gonna be the same. Air's, the volume on a fan is a constant volume machine. So if you take any given fan and you stick it up on the top of Mount Evans and you turn it on, it's gonna move 2,000 CFM. You bring it out to Arizona, you put it in Death Valley, it's still moving 2,000 CFM. It's just moving a whole lot more mass of air. That's the difference between actual air and what we call standard air. Okay, so here's the quiz. So this is class participation. So what's wrong with these pictures? Okay, so we got an actual flow fan here, right? You want to filter it. So what do? They put the filter right up against the fan, right in the blast area of the fan. Actually, this is the suction side because airflow on this fan is, on this filter should be this way. It doesn't have a support grid on this side. You can see the support grid through the material here, so that's to keep the filter from blowing out. So we completely restricted the suction side and the inlet side of the fan. Bad system effect, right? So that's somebody's idea of filtering that air. But here's the scientific approach. Put a lab coat on and same damn mistake. And you've got a genius here. Okay, now, check this out. This is real life. I'm on a job down in Arizona, and they put inlet filters on all the fans. They're killing these fans. You're choking the fan. Here's that system effect. We talked about the length of the duct on the inlet side before you start choking it off. There's no duct over here. You're in this high RS system effect on this thing. And you see this stuff. I see this stuff every day. Here's another one, system effect. We're coming directly off these fans, and well, this one's got a little bit of riser on it, but it's also got a larger outlet side here and restricting the outlet sides right over here. We've got these short radius elbows. We've got restrictions on these caps that somebody designed. Obviously, they did that on a bench in the equipment shop. Lots of difficulties with this system. How about this one? You guys all deal with this stuff, right? So I'm at this hospital, and I can't.
Any of these roof lines.
Nobody here should recognize this, but so what does it say here? It's a biohazard. They got their maintenance guys, they're just going up on that roof. This thing should be 10 feet in the air easy if you're going to turn it down. You're not supposed to turn it down at all, but it's supposed to rise up 10 feet and discharge straight up, right? So check this out, though. You've got inlet movers over here on the roof. You got a biosafety hazard fan over here, got a sticker on it, or radiation. There's a biohazard over here, and you got this nice little duct over here and a building over here. I apologize for this picture being washed out, but it goes right down here. So this guy's up on the roof. I poke my head out and say, hold on, I gotta run down to my gig bag and get my respirator before I go up there. Here's another system. This is the same fan, two different views of it. So this is looking at this fan from the side that I'm standing on over there. And look at the way they're doing this. They're changing the direction of this fan and the dimension on this fan right here, right in the inlet cone instead of 4 duct diameters downstream.
But Bill, at least it's hard duct, you know?
Yeah.
They use a dryer vent.
too.
They use a dryer vent to transition.
So here's what the problem obviously is with this system. Okay. Fume hood. Yeah, equipment's way too big. It's right up against the face of the fuel hood. Got terrible air entry pattern into this thing. You guys are supposed to be telling me this because it's part of the quiz, but, I just point out a few of these. What about this one? This is a mess. So this lab, they got a supply
Sash way too
diffuser
high.
in the ceiling right over here. Louver face supply diffuser, 24 by 24, 800 CFM. And they're just coming down here, wiping through this hood and pulling the contaminant right out. There's another one for you. That's a beauty, huh? They operate this way. They're cooking stuff right here. I think they had to move it from here to here. Look at that. There's an auxiliary air hood. Right, so they got a plenum in front of the hood here, discharging air down. So it was too cold in the winter, too hot in the summer, so they disconnected the auxiliary air. And look at the spillage they're getting. Oh, no, I'm sorry. This is when they had the auxiliary air running, and it was pulling stuff out of the hood and corroding the whole the airfoil and the perimeter of the hood.
How are their lungs?
Yeah.
So here's one. This is a fun one. So they had this on a fume hood, and the guy told me, I don't know, it worked last year. And so we measured some face velocity. Yeah, they're low. Looked at them from last year. They're low. And so this is one of those cases where actually you had to have some tools with you, including a lock, so lock out and tag out the system, go up on the roof, open up the fan, scroll, and the fan wheel. It's 60% obstructed. Here's your flex duct stuff. Here's a couple of them here. First off, they couldn't figure out why they weren't getting air out of this system down here. And if you climbed up the stairs, not even a ladder, stairs, up onto the catwalk, I had to just take a little pair of pliers there, open that, lock it up, open up the latch gate. And wowie, you got air. Take a look, right? Insufficient airflow. Here's another one, this is good. Flex duct. Flex duct is the worst. Terrible configuration here. Not only that, but when you're moving air like this, you get all this friction on the side of the duct, the stuff starts building up in the bottom of the duct and blocking the airflow. The good part about that is it increases the velocity there and it tends to pull some of that stuff out. Here's another one. Flex duct. So just connect point A to point B and now here's one. Hope nobody recognizes this, but variable flow fume hood. We were called in because there was goo coming out of the hood. Like a technical term for you. Goo. I'm not going to say anything else about this. Gotta be a little careful. Okay, so here's another. This is a mine site, and in a hot climate, and they put these coolers. This is a back cooler. It's got a section on the back here that's got cooler pad and a pump, and it pulls air in and blows it out here. And they put this. This is the size of the room. You know, from one lab bench to the other. This is a sample prep lab, so there's grinders and crushers and stuff. And they got this thing blasting about, 700-800 feet a minute out. This thing blowing it right down the aisle in between these, and it's just sucking everything right out of the hood. Classic example of room turbulence. Here's a lab, same one that had that rusted out fume hood in it. They're getting a lot of dust in the building, so instead of putting filters in the air handlers, they put filter racks in the the ceiling, and they're trying to blow air through 1-inch pleated filters. What do you think about 1-inch pleated filters, Mike?
Choke the system down, Bill.
The worst filter ever made, 1-inch pleat. Because any system that only has a 1-inch rack can't handle the pressure drop of a 1-inch filter, pleated filter. Anyway, you can see what happens. Blows the filters right out of the rack. And then,
But does that mean I get to sell more filters?
please,
Yeah.
put some 2-inch filters that go up the unit, retrofit it with a decent filter bank and change it more often.
Oh, but the dirtier they get, the more efficient they are.
Yes. And they ride backwards on that RPM curve, right? You ride up that static pressure curve, the bit air is dropping off, and further you go from right to left, the less air you get. Okay, there's turbulence in a, metalworking system, but they had all of these canopy hoods over these ovens over here, and high metal exposures, metal fume exposures in here, and yet they had the supply duct running along this wall, and these registers coming out, louver face registers. Louver face registers don't belong in a lab. I'll show you pictures of some radial flow diffusers if you have louver face. Oh, I'm sorry, here they are. There's a radial flow diffuser, kind of like a big semicircle here, all perforated face. Increase the face area, you get velocities down to 50 feet a minute or so. But here's another lab. No, this is a manufacturing facility here, and has sidewall diffusers blowing straight across where these canopy hoods are over the, discharging metal grindings and stuff into these barrels, and it's just blowing the stuff all over the place. Another big lab. And so they have, these are 2 different locations in the lab, and in one, they got all of this open area here, and they're pulling stuff off, but they got some diffusers up here that are blowing down and breaking up the entry patterns over here badly. But here's the same lab, and they did it right here. They put enclosures around this stuff. And calculate it out to 1 foot in front of it, but it's just a bad.
Yeah, when we give a report like to Denise, and she'll say, well, you just said it's smoke's retained, that's meaningless, I need numbers, give me numbers. You know, and
I wouldn't say that.
I'm thinking I do. And so I don't know how you quantify whether something's working or not like that.
You know, you can use a hot wire. I hate hot wires. I don't trust them as far as I can throw them, but you can use a hot wire and pick out increments from the face of the hood, 6 inches, 12 inches, 18, at 18 inches, you're not gonna get anything.
But on a single source, point source exhaust, like with the formalin, you just monitor for formalin.
Yeah, well, you can measure the face velocity at the inlet of the hood, and then work the formula. It's a very simple formula, and you can determine how far away you can put that to maintain whatever face velocity, whatever capture velocity you're looking for. That's a lot more.
Well, that's it. And then I say, well, what velocity are you looking for? I can give you any number you want. And you measure it and say, oh, that's 80 feet per minute. We just write down 80 feet per minute and hand it to them. We don't know whether that's what they really want or need.
Yeah. Well, that's the thing with laboratories and stuff, especially with fume hoods and that. What velocity? They say, well, it's supposed to be 80 or 120, right? Isn't that what all fume hoods are supposed to become? Huh? There's nobody that said it's 80 to 120 anymore. It's whatever you, the operator, determine you need for your particular operation. And then you work with your certifier or whoever's your balance contractor, whoever's working with that, and you determine where you need to be for your particular operation.
Well, but for a lot of us in the room in academia, we don't have that luxury, right? We often have to go with a range because we're not there to say, that sash, that big thing in front of you, it needs to be down, right, to capture. So you don't have the benefit or the luxury that you often do in a private setting where they need to follow protocol. In academia,
Well, somebody
You
needs
still
to
have that.
establish your criteria.
well, it's established, Bill, but whether or not it's adhered to is another story. And so it's not as clear cut. We'd love it to be cookie cutter, but it's not.
Well, it's not that way even in
Industry.
private industry, because they don't know what they want. They've heard 100 feet per minute, back to fume hood discuss, 100 feet per minute. How do they know? They
The
don't
more have to
know.
follow
Yeah.
the procedure.
Came up with that magic.
Your sash is going to be at 18 inches.
That stuff's all gone now. It's not in the D9, the 9.5 standards anymore. There's no prescribed velocity. We talked about insufficient capacity, loose belts and stuff. So I said, it's like they smelled something burning downstairs in the building here. And there's all this burnt rubber all over here. But look at it. There's the idler pulley over here. It's supposed to adjust the belt tension, right? It's just kind of draped over it. They didn't have the right size belt, so they just, whatever they got, they threw it on there. And they're burning belts up and they're not getting capacity on the system. More system effect factors. These are all real life stuff. In all fairness, manufacturers put these dampers on fans like this so that you can condition your bags in your bag house or your filters in your dust collector. Because when you first start the fan up, it's going to be overloading the fan, but then you condition your filters by feeding some conditioning agent, sometimes it's Portland cement or something in it, and get it into a back pulse situation. You've got your filters conditioned. Now you can open the damper back up, but you don't want to leave a damper, operate a damper right here in the blast area of the fan. Here's another one that we talked about, these configuration arrangements, and we got this fan that comes up like this and goes back down like this and over. So really, this is the discharge of the fan, and this is how far the throat of that elbow is, right there. 8 inches or so. This thing should be 10 feet up, or they should have selected a fan with a different arrangement. They could rotate this fan housing so it's blowing out this way, and it comes right off the fan and goes right into the rotation. So there's ways of doing this stuff right. So here's one that's got good and bad stuff. This slide's washed out too on this thing, but so here's a good elbow, nice round, even radius on this elbow. Configuration here with the transition and the bigger and the inlet there. But here's that one that we saw before, right? This is real life, is what you see. And then here's flex ducts on all of this stuff. This is a killer. This whole arrangement is 50% probably of the capacity on this system. With all this flex, this stuff bent like this, and with this turbulent air entry pattern. Here's erosion on a fan wheel. These are balance weights that they put on, but the balance weights are almost eaten up completely, and you can see how the blade is being eroded here. And we see this a lot. It's to be expected in a lot of applications that your wheel is going to erode. Here's a variable pitch blade that
Developed quite a
that built up a lot of material on it, threw the blade out of balance completely, and they lost the
Yeah.
bearing. Here's some more system effect. If you go back to that other page here, we look at these diverging fittings over here, and then you go back to this one and look at this. Look at these fittings here. This is real life. And so, and then this is the inlet. There's a screen on here. The screen's completely plugged up. So it's got bad inlet side, bad discharge side system effect. Here's one here. This is actually opened up. There's so much stuff in there. It's almost completely plugged up. And this is my favorite, the poster child for what not to do. So we got this high pressure blower here. We got about 15 feet of flex duct down to the floor to pick up the carbon monoxide, because carbon monoxide always goes to the floor. And then we come right off the discharge in the blast area. We put a 90-degree mitered elbow or a box elbow on here. Then we run the flex duct 3 stories up through the roof. So this connect point A down here, the point B up on the roof, and that should do it. The other interesting part about this, I certainly won't tell you where this is, but this is alive. Look at this stuff. This is chilled water lines, glycol lines. They're insulated. There's water dripping off them anyway, and running down the side of the concrete block here. And it's just yummy.
UV lights.
Yeah.
Thanks, Bill.
Thanks, Bill. Thank you, Bill. Before we get to Denise, we'll take a little break. Go use the restroom, get something to drink, any more food. We'll come back in 5 or so minutes and we'll let Denise do the presentation.
Did I bring the over?
Okay. Yes, sir.
Thank you. What's that? No, I want to.
For you and the husband. Oh, thanks. You're taking a break.
Oh, for Casey too?
Yes, thank you. I have it. I'll be right there, guys.
You can take that screen.
Well, when you said 11,000 feet up, that's right after, when you're going up.
Yeah, none of those pictures were. 11,000 feet up, so, yeah.
Yeah, well, right, okay, right, the ocean one. But then their sister company, Anderson.
Well, it's all the same company.
Right.
Henderson, they have the mine on the one side, and the mill on the other side.
Right. And the shaft is on the, is going up, further. So that's why I wanted to say 11,000.
But that isn't 11, the Henderson mill is. None of those are the line.
When you
It's
get
on the.
Well,
it's on the-
it's still taking a few months.
Yeah, right.
I'm running out of pork.
And
Yeah, it works
that's
out really
about,
well.
about 8,500 feet.
Yeah,
You're
that's
welcome.
The top three paths, that's 11,4.
Yep.
And
Oh, I'm sorry.
they had
Yeah, no, there's no quantitative way to show it or something. I have never seen it. Visual smoke, yeah, you can see it's going there, but it's.
And you know, we went with some hard numbers, we went with some hard numbers. It was, you know, for King Joking, you got that sash protection. And we wanted, you know, around 100 to 120 because you know, it goes up to the sash.
Yeah, no, I get that.
That's all I just need.
Plus you've got-
One of the systems.
You know, then you get together to wear one. But the tourists, they probably went to the older.
Temple guy in Arizona, and I worked with them.
All these other changes.
Lower dust collector.
One of the first
Primary move
yeah.
is a dust collector.
Is, well, my piece of equipment fit inside the,
Yeah.
right?
Yeah. Got an oven
And
this big. Oh, yeah, it'll fit.
And-
Squeeze it right in there. Barely pull the sash down.
And it's always, I can say it, moving.
I have it. It's,
And you know, a lot of the guys,
these engineers,
they're around
it's running. Everything's running.
Yeah, you
I got a little. So I get to get started.
You gotta be the-
The old truck up to the right. And then it
And I
just
want
turned.
my
Yeah,
four.
Yeah, I will watch.
There, there.
Okay, so I have a question for you.
Yes.
So I had this conversation with my HVAC.
Turn it off.
Back and forth.
Gradually slows down.
So-
Until it's really straight.
In our lab,
Yeah.
one of our labs,
So it should go.
we have two GEs in that lab.
Change your wires.
And they are not using the units, but they would like space to be able to use the space for this unit. But they don't want to take the hoods out because they're expensive to put in and out. So we had this conversation about whether they can just, we can just turn the fan units off, but the junction off for those units. And, you know, so then they can keep the sashes open and stuff and that. The guys are like, no, we'd have to rebalance the whole roof. My logic is, why would you have to rebalance completely? Because theoretically, you balance the room with the fans with the hoods closed to begin with, not sucking in the air. When you bring them up.
Well, there's a lot of issues.
Okay.
The first thing you really know is are they variable values or they constant value?
Being they only need as much as they need.
So a variable value, look, if you lower the sash, you reduce the air fluid, you maintain constant base velocity.
Right.
And then you lower the hood all the way. It's gotta maintain X amount of CFM per square foot of hood surface. So if it's an operational hood.
Okay.
But,
But in that description right there, that's a lot.
So I'm gonna try to get through.
the hood might be sized for 5 hooded CFM. You lower all the way down. The number
Some of the handouts.
10%.
It might be low.
So,
No, it's a function of the square footage of the house. So if I just turn it into the 2.5 feet by 6 feet, you have a 4 square foot bed stop. And you have to have CFM and the minimum flow. So, and one of the things that happen is that one is there is some kind of controller on the hood that senses the gas condition and reduces the flow into that hood. And it's either Venturi, that also or blade type thing. Either one of them is gonna give you so much flow with the alley.
Right.
You don't have to get anything special. Also,
they stopped it all like.
And there's gonna be
Oh.
or like,
So it had to have enough in there.
that's gonna look at the flow of the impact in the position of my three valve. And it's gonna tell the building HVAC system to slow down the amount of air.
Yeah.
and to relax. You don't ever want to get to that poverty. So constant volume from in the room. Now you're gonna pressurize that room and stuff.
A number of years ago, I was in charge when I was at the University of Georgia. We had a marine station on South Island, which was, I don't know if you're familiar with South Island, close to Georgia, hardly around its own island, and there's no, way you can get on there is by boat. And so, a few months there, they out of plywood, and they had problems with the moisture and everything, and the expansion rate. They actually brought in granite. And they just used it out of granite. So they made box and they put yeah, out of granite.
People sit there, yeah, I was talking to sit there
Over.
that's what I would hear, just see everything.
So the long and short of it is,
The first question you get from every season is, will my basement fit inside?
system in there.
There are 50 million feet back there. This is a newer building, so it was constructed in 2011.
No, we had gas grills in a few moods.
So, I mean, the building
Seriously.
was set up.
Chances are it's probably the design of
Usually
the Georgia.
it's
gas
all,
grills in there.
we've got 50 million back in place to HVAC, they control.
So Peter, you're
They can tell them, they can tell you what height.
been there a month.
What height.
Good.
Based on the airflow, they can tell you, what your stacks are up or down, they've got extra stream. I mean, we're talking a lab that's,
You got some relatives that live up like Lead
we're
Lake.
talking a lab that's doing that glass.
Parts.
But so we're using this table.
So, but you have the same position as you do here? Yeah.
But our sustainability guys are HVAC.
Yeah, it's quite different.
Well,
I know states with all
it's
the-
this,
So I had it in there.
shut the switch off,
You had it.
without
That nuclear reactor
really
is so
messing,
critical.
without
The
messing.
new drive.
I'm not getting it, guys. I am not getting why we have
Blow box
to.
operations. So you must add some like acceleration.
Yeah.
Association
But
with
there's
ADL.
each
Yeah, we had a joint research facility.
As I understand what I have to do.
Yeah, we got some, America actually has a group that does nuclear
Each one of those labs.
kind of stuff.
Yeah.
Yeah, I
Each of those
know.
labs
Yeah, with the glove box
has
people,
each
it's,
one
the ones that are associated with DOE,
Yeah,
they follow the DOE requirements with glove box, because they get a great, it's a $500,000 glove box, but it's wonderful. It's got the best system. And then you get the people that aren't affiliated with fly with the DOE, just, just to use the filters. Or yeah, and then trying to help filtration.
We had never had.
Yeah, big difference between commercial military grade. And then before that, was Georgia State, because the SL4. This one's Georgia State.
Ready to do some
Dental work, so the UGA is important. The arc. Yeah, they started building down. I know they have ABSL3, ABSL4, ABSL3. You know, we got those. You can move on what you have listed. So I've taken out the not all. No, Georgia State, we have 3 sites. BSL3, BSL4 select agent, racers. And then we're building a new site that uses I don't want to say I am and so it's good. We'll see if but then they got that was the okay. So point is that both has a great experience. To have you in the group. So I want to something you guys do this presentation. Yeah, it'd be a lot of fun. I got a diagram. I can know if I need to be. You know, when I was working at Georgia State. Well, and I just, what is Biomark doing with these people? Zeke had a couple other things. He's on nuclear power because I wasn't going up, putting out a mask on. I was pulling these things out. I got my face in there. And then it's gonna be like us. Like this.
So, Jared, it's been invited you, right? Teresa's, yeah, I think I
Then,
saw.
the two young guys, and then I can't remember.
I was thinking about seeing the meeting last week. And your sister, got 4 scholarships.
Why is this old man up on the island? You guys are down there.
Yeah, I know. That
In the beginning, they were so serious that they're
There you go. I think that is a big reason this,
loosen up on the marker and ladder guy.
Yeah, it's not. Is it?
Yeah.
Because I know that some people in ISU want to.
Yeah, those should be okay. They're suppliers.
Yeah, yeah.
Because
That's what I,
that's what they
I was
wanted to
gonna
do.
say,
Like
there's
a Skype thing.
chapter up there.
I know, I'm doing this, right? I got my tape measure out, I'm doing this shit, and I go, in my mind's eye, I go. Right, so you get the-
There wasn't one there. I think the closest traffic was-
I'm trying to get the building. So those guys,
It's asked about it.
I found one that was not
Yes.
accurate with what the package is.
And I'll connect you to recordings.
Yeah. Great, yeah.
It was an 8-inch shot. 13, 16.
When I was listening earlier, because I checked it from the.
I know National Jewish Community Law, and you know what they
I checked it, it's a board meeting, it was fine. But as long as we don't want some feedback, I can probably check it right now. Because when I turn my speakers on, we get horrible feedback. Yes, we are going. Stop and try and get us going again, if that makes any sense. So talk to me. I'm not hearing that at all. I'm not hearing you hardly at all here in the room. Okay.
So it's on.
Yeah.
How about now?
That's much better. That's better.
How about now? Was it recording okay?
Yeah, you may want to just turn it up just a little bit, Jim, if you can.
How about now?
I think we're okay.
Good, okay.
Mm-hmm.
Everybody? This is Denise. She was the other one who graciously stepped out when everybody just fell apart at the end. So Denise, thank you so much for stepping up and doing this, and Denise is gonna give us a little how-to on how to build a biosafety program, so.
This is the first time I'm giving this talk, and a lot of it came from, when I developed this really on the fly on a board call, was thinking about the feedback we've had over the years, where we've tended to focus our training topics, certainly in the beginning years, really around select agents, and select agent programs. And, it was just, I think it was just the timing, 2008 through maybe 2012, where there was a lot of things going on in the select agent program. It was just every time we met, there was something else coming through on the regulations. And unfortunately, a lot of our members, and I think it's probably true today, don't work with select agents or do BSL-3. So today's talk is going to be try to be more of a nuts and bolts talk. I'm sorry.
I can't quite hear that.
So that's, I'm hoping that you guys can walk away with some tangible tools that you can take the concepts presented here today and shape them for your own program. And for those, hopefully this will be a bit of a glimpse into our world, our end of the thing, so that when you come to certify biosafety cabinet, you're called in for ventilation consulting or engineering architect, design and building your building, you might have a better appreciation on what we're trying to manage, right, of the equipment or the use of the equipment or building design on our end as safety professionals from a day-to-day operational standpoint. So hopefully that'll come across to you folks as well. I'm going to be passing out some documents that I'll be presenting on the screen. I don't have enough for everybody, so if you can glance through them, pass it around. I think it'll be helpful as I'm going through and describing certainly this first document, which is a biosafety protocol or application. All of these documents are going to be available on the FRaBSA website along with the presentation. And hopefully we can start, my hope is that we can actually start maybe a little resource library where we can all contribute documents of programs, programmatic elements to this space so that we don't have to reinvent the wheel when we come across a need for a biosafety cabinet program plan or how to handle HAZCOM and SOPs, things like that. So I'm just going to go ahead and kind of hand a couple around. But you'll be able to print these off, they'll be PDFs. Okay, so let's get started here. So how do you, what are some of the things to try and keep in mind when you design a program? When you're either looking to revamp your program or start from scratch on an entire program or programmatic element. Well, I think of things, three important factors. There's more, but these come to mind for me. It needs to be flexible because in our world, we're under the auspices of regulations, right? Policies, procedures. If you're working in academia, you're really at the whim of the research curve, which is constantly changing. So your program should be flexible, right? It should also be scalable. For me personally, I learned that from going from the Boulder campus to the medical Anschutz campus. So Boulder Research University has more students, more researchers than faculty. Whereas at the Anschutz Medical Campus, we have probably more faculty than we do, graduate, postgraduate, or fellows, medical students. So the program at Boulder might have 125 principal investigators. Down at the Anschutz Medical Campus, we probably have closer to 600, right? So things that I might have wanted to introduce to Marcia or to Terry when she was there, that we could take from Boulder campus and implement it at Anschutz, it had to be scalable. And that also goes to if you have, you're working in a clinical setting or public health lab and you've got, I don't know, 20 people. Well, that's today. What about 5 years from now when they take on another clinic or, there's something that they need to scale up? You'd like to know that your program or programmatic elements can grow with it, with ease, right? And then the last thing is sustainability. You'll hear a lot of things that most people have heard me say over the years. I like one and done, right? Especially if you're an army of one and you don't have a lot of resources. Even if you do have more than you're not an army of one, you're somehow always limited on staff. So if you can get something that's sustainable, that you've developed, you've worked out the kinks, you've road tested it, it's nice to know if it's sustainable. Okay. And this is informal, so I'm going to be asking you guys some questions. Feel free to ask me questions throughout the presentation. So another thing I like to say is you can't manage what you don't know. You could manage it, but it's probably not going to based thing. The inventory, but if you're not going to do anything with it, or it's not housed in a program or programmatic element that can be useful, maybe you just don't need to ask for it right now because you're not going to be able to do anything with it. So you have to prioritize, right? Biosafety cabinet, same thing, we just talked about that. Autoclaves, depending on how you handle your waste. And then biological waste. And again, this is not an exhaustive list, it's just some things to think about. This I actually took from Boulder. And I'll talk to Holly to see if it's okay to put it up, or I can modify it as a generic. But basically, this is an annual update questionnaire. So it asks some simple questions. Of course, it's specific to the principal investigator. I'm sorry you can't see it too well. We ask, who's the PI, the date, the department that they're in, and give us what we do is an IBC application number and authorization number. So you'll find you want to think about unique identifiers. Okay, so a unique identifier for something like this would be the application number, right? And that alphanumeric and specific, maybe not only to this form, but it ties it to the PI, the date it was reviewed or the date it was approved. So when you design some elements, sometimes you need a unique identifier, especially if it's all going to be electronic. Okay. And then ask really two questions. Right? You say, give them a little explanation of why we're asking for the information up here. You give them some links for, generic emails and where to send information or ask about, have questions. And we just say, look, is this work you submitted 2 years ago or last year? Are you still doing it? Maybe they are, maybe they're not. So they're going to tell us yes or no. And if yes, has anything changed? Well, maybe they've added some new infectious agents. Maybe now they're doing the recombinant DNA work that they weren't a year ago. So then we say, okay, well, look, if things have changed, you answer yes, you're going to need to do an amendment to your protocol. So for us, our protocols are good for 3 years. A lot can happen in 3 years. So you might want to think about, some folks do this annually, they require it annually. But again, you have resources. If you don't, you have to go like a 2 or 3 year. You may want to do just a simple update form. It just checks in with them, one, to see if they're still on campus or still in your organization. Are they still doing the work? And has anything changed? And then the second one, which is the most popular, is tell us if the lab personnel have changed. And this was like the most important feature of this form for me, because I had to keep people trained. And I said earlier, like at an undergraduate, it's one of the biggest challenges. And then they sign it and they just email it back to us.
We actually do the personnel update every semester because we're an undergraduate institution and we push undergraduate research. So my researchers in my labs change literally every semester, if not more often. So we actually, about 2 weeks into every semester, I send that out to all my PIs and say, not just my bio PIs, but all my PIs, and say, who's in your lab this semester?
And this ties right back, you can't manage what you don't know. You're trying to stay compliant, let's say around training. How do you do that? When they fill out the lab personnel table, is good for that day.
You hope.
Right? So this is just another tool to think about that you can do as an interim to try and have this, continuous oversight. Easier said than done. So now I'm going to talk quickly about Biosafety Cabinet Program. And this will make a little bit more sense after I go through the next slides. But like I said, we first did a field verification to know what we have that we have to manage. After we did that, or while we were doing that, we said, well, let's issue each cabinet a unique number. Okay?
You make a typo in serial number.
Yeah. Serial numbers are anywhere from 6 to 12. numbers and letters. And usually it's very difficult to even find the serial numbers sometimes on these cabinets and transpose the numbers or letters. So we said, you know what? Let's go to a unique BSC number. So every cabinet's issued its own number. It goes on the front of the cabinet. It's highly visible. And the other thing it does is it really kind of gives ownership. Sounds crazy, but this stupid little sticker with a number on it, now all of a sudden the researchers go, well, my cabinet's 47 and 48. Those are my cabinets. As opposed to you say, well, can you tell me, is it serial number SNJ2657B8? I don't know. I got issues with it, right? Now you can say, well, tell me what number it is. Because I'm sitting at my computer and I can look up in our system everything you want to know about this cabinet 500. When was it last certified? Were there any issues in the last certification? Is it due for certification? Agents, what PIs are using this cabinet? And then you can look and see what the research is that the PI is doing. Right? So there's a lot of information to give. See, stupid, but it's not. It's a smart stick. Smart stick. Okay. And keep in mind, think about this: if you have autoclaves you're in charge of, animal transfer stations, fume hoods. I've used it for all of this. It works really well. And again, it's rinse and repeat. Same way you manage your fire safety cabinets, you'll be able to use this for your fume hoods. You'll be able to use this for your animal transfer stations, your autoclaves. The other thing we do is we put a removable card, again, on the front of the cabinet. And this is to begin kind of closing the gap of information between the cabinet that's sitting across campus, us sitting back in our office, and wanting to know who uses that cabinet. Because again, they tell us on this form what cabinet they're using, but this is what? Every 3 years. A lot can happen. So we put a pocket on the front of it with this removable card, and we ask them to please complete, the principal investigator's full name, their phone number, and the date you completed it. And there's a little QR code, okay, that will take them to a web-based form. And there they can add and delete a PI. Close the gap, okay? And then we put a little instruction that we taped up there to kind of introduce them to this new concept and tells them a little bit about, what to do, that we're looking for the information. Please visit the website or the QR link to fill out the form when we add and delete a PI. And that's what this little instruction goes right up there. Okay? And then this is the form again, the little QR code or the web link will take them to, and we ask some basic questions. Are you adding or removing a PI? Just check the button, the radio button. Tell us your BSC number, so we know, because everything's attached to this now. Give us the PI's name, first name, last name, the phone number, and the date, and got a little comment box if they want to tell us anything else.
So do you collect that information through Excel or SharePoint?
This is SharePoint. We use SharePoint.
But it gets entered into our EHS database.
Right. Yeah.
And I think we're fat fingering it, right? It doesn't-
We are. There's no interface.
Yeah. That's what student work is for. Yeah.
You can do the same thing for an autoclave program, like I said. You issue a unique number, and for the state of Colorado, we're required to have a method to measure the effectiveness of our disinfection program. So what does that mean in English? You're using an autoclave for disinfection. How do you know it's working? Well, routine maintenance, right, to make sure it's meeting manufacturer spec or operating manufacturer spec. You do a sport test on it. So this is an example where, again, you would issue, you record the autoclave number, the year of the building room, the date of the sport test, because this is for sport test, who did it pass, fail, any notes. I like visual, so that if you go buy a piece of equipment, or let's say it's an engineering control, everything's right there, so you know when it was last maintained, you know who's working on it, who uses the cabinet, right? Everything's right there in front of you when you go to that piece of equipment or engineering control. I like that.
Questions?
Yeah.
So your student workers go every year and put a new blank card in, what the old, or?
So, I'm not sure what Holly's still doing for the autoclave.
It's a little bit different than that. So we go on a regular rotation just to check and see. I mean, it's supposed to be every 3 months, and then 6 months for maintenance, but we just make the rounds and frequently.
You can always put an extra card behind it,
Yeah.
you know. And same with BSC, you know. So when we had our student go around and do field verification and set up the hood with the number and this, we had them put a blank card behind it as well. Okay, so HAZCOM and SOPs. Here's another example of, you know, trying to get a handle around hazard analysis and risk assessment, right? Here this is an example of doing animal research and what are you putting in it, what are you introducing into the animal. For us, we kind of worked backwards. We knew we had to still meet the goal of HAZCOM. We wanted to standardize SOP so that our vivarium staff knew what was going on with the animal, what was going on with the drug, chemical introduced. But we worked backwards from waste streams because we had a big challenge in front of us. We have huge animal research numbers at our institution, both small rodents and even some ag animals, pig, sheep, calves, occasional goat. Fish, yeah. And we have 2 vendors that handle our waste, and they're very different vendors. One is a pet crematorium, a local crematorium, and the other is a vendor that will take carcass that has hazardous materials introduced to it and bring it non-RCRA, hazardous like pharmaceutics, chemotherapeutics. Well, I shouldn't say that. Hazardous chemicals, drugs, compounds, non-RCRA, and it would get incinerated to Fargo. So how do you manage 2 different vendors of all these different kinds of drugs, chemicals, or compounds? Well, the first thing we did was we narrowed it down and we said, okay, the commonality or the common denominator is that it's going to be a drug, a compound, or a chemical. And the other commonality was it's going to only be introduced in the animal probably 3 ways. Directly into the animal, and that means IPIM, inhalation, right? Gavage, ingestion, that's one. In the water or in the chow. We said, okay, now it's become a little more manageable. So we said, let's create an SOP system around that, where we know these 5 categories, we can separate these out by vendor. So for instance, if they introduce an antibiotic, a chemotherapeutic, a hormone, or a non-hazardous drug, compound, or chemical into an animal, it can go to the crematorium. If it has what would be categorized as a hazardous drug, chemical, compound, it has to go to our other vendor and get incinerated. Okay, so we said, okay, we've got that, right? Now let's address HAZCOM, right? So we created a template, an SOP template, because the other challenge was it can only be 1 page, because the vivarium staff have to print it out, it can only be 1 page, and post it on the door. So it's okay, we can do that. We get a fillable PDF, and I'll forward this a little bit so you can see better. So here you can see the researcher that's completing these. They submit an IAPC protocol, which is the Institutional Animal Use and Care Committee. They list in a Topaz form, which is just like a biosafety form, but electronic. They tell us what the research is. They tell us all the experimental agents. And then we've given them some aids to determine of all the experimental agents, where do they fall in those 5 categories? And how are you administering it to the animal? So if they say, well, I'm using gentamicin, and I'm giving it directly into the animal, I need to go to the template that's for an antibiotic that's administered to the animal. If it was gentamicin that they were putting it in the water, they would pick the template that said antibiotic administered in water. Now, the top part of this I'm showing you is specific to the administration, the type of administration, and the specific drug, chemical, or compound that they're using. So they have to complete this. And it does cover HAZCOM. It tells the hazard class that it is, the task number, the dose or the route of administration. Is there any expected excretion, right? What are some of the hazards associated with it? And then what are symptoms of exposure? So we captured that HAZCOM piece, right? Risk analysis and HAZCOM. Then the second part, and this is where we got the most bang for our buck, is we said, well, we can pre-populate all the things we care about. We care about safety, right? But the things in terms of how do we tell people how to get rid of things the right way? How do you get rid of the bedding? How should you handle the cage? Do you need special PPE when handling the bedding or the carcass, right? Then how do you get rid of the sharps, the bedding, the drinking water, the chow, carcass disposal? And this is pre-populated because this never changes for an antibiotic administered into an animal, right? So we ended up essentially with 15 templates. Why 15? Well, you have 5 categories and 3 ways of administering it. 3 times 5 is 15. So you have 15 templates, but we never have to go in and answer this 50 times for everybody that uses tamoxifen and administers it in the animal. Because we have to fill this out 250 times. Now they just have to select the right template. This is already done. Now this concept can be applied to many different things. I just gave you an example for animal research, but you can apply this to a number of things. Okay? Any questions on that? Waste management, that's another big thing. Well, even if you're using a vendor, you don't autoclave anything, you don't do chemical disinfection, the vendor shows up and picks it up. There's still some things you need to make sure are getting done, right? You need to make sure about segregation. So just because you hired a vendor, if they have a packaging set up, let's say it's a plastic tub or a box, that packaging is rated by DOT. You go out on a public road, it's only rated for certain things. So let's say it's only rated for solid waste. And you've got somebody that's put urine cups in there, full of urine. It's not rated for that, right? Tubes of blood, HPLC samples, histology preps that have, a liquid associated with it. So even though you have a vendor, you want to be on top of your waste streams, okay? You've got DOT to contend with because it's going to go out on the public road. And then you also have state health departments. So I can only speak to Colorado, but this is where I was saying about, the state health department. They have things like notification of where that waste is being stored. You have to have a biohazard notification. It has to be in a secured area. There are requirements and regulations around how you handle that waste before the vendor picks it up, or you put it in an autoclave, or you apply chemical disinfection. Okay. Same with I said about Colorado State Health Department says you have to have a method to measure the effectiveness of your disinfection. Wyoming, I'm not sure what your rules are, but there are state rules as well as federal, so it's not just DOT. Make sure that your waste vendor is meeting regulations. And then regulated medical waste does require DOP standardized shipping papers, or what we might call manifests. Okay? Again, make sure your vendor knows that and is following that. Because if they're not, you're still on the hook for fines. We know that. So this is shipping papers, and I did a blow up on that. So here's our vendor, MSDI, Medical Systems of Denver. We use a unique manifest number for each one so we can track it cradle to grave and also for invoicing purposes. We ask, each one is issued, we do it by building or off-site entity. They're issued their own account number, customer name, their address. And then this is the language here for DOT. It's, who's the generator, who's the transporter, where's the destination of that waste going, which is to the vendor in this case. Emergency contact 24/7 has to be available. And then there's specific language pertaining to biomedical waste or regulated medical waste, which is UN 3291. And every comma, dot, and space is specified.
God help you if you don't get it right.
Yep. And so we put it in there we complete manifest on campus because we have our own techs that pick up our waste internally before it's turned over to MSTI. But we have 40 off-campus entities. It's like herding cats. And I'm being generous when I say that. They need to provide a weight. Well, clinics don't have scales for waste. So we had to come up with an average of a red tub waste, a yellow tub waste, that they could just enter it. Right? Every container that MSDI has its unique identifier number. Where did it come from? And then a double check as to whether it's a red, yellow, or yellow animal. And then at the bottom, you have to have a generator certification and use the specific language out of the regs. So all of this shipping papers is in 49 CFR 173.24. Okay. And then the generator has to sign it, print their name and sign it, and then we ask for a transporter to print their name and sign it. And it's done in a duplicate. So, actually, I'm sorry I didn't pass these out, but so here's some samples of the manifest and the SOP. You guys can take a look at that, pass it around. And again, these documents will be PDF files up on the website. And that's it.
That's all you need to know.
That's all you need. And that's, it doesn't cover, the programmatic elements that I talked about is in no way exhaustive, right? There's plenty more programmatic elements that can be developed, right? There's just no end to it. But again, can you sustain it? There's nothing worse than spending all that time to design and develop it, you put it out there, and you just don't have the resources to maintain it.
So if you were working with plants, you have researchers working with plants, that's a whole nother level. It's like a whole different biosafety program.
Just like arthropods.
Arthropods, yep. So, yeah, I mean, they get you have to cover those same kind of elements, but there's specific regs and requirements that you have to be familiar with for those areas.
And that goes to Brad's point, is that, if you're going to build out a specific element of your program, right, you may want to think broader, not only beyond what the scope is today. So no one's going to use arthropods, but you've been hearing that there's the latest and greatest funding out there to do
Mosquito work
there. I was going to say Zika, right? And think, what? Maybe I'll hedge my bets and figure out a way that I can design this to meet today's needs. But if we had to add on arthropods, we could do it easily.
So in our animal form, we ask you, are you going to work with the arthropods? We don't have anybody doing that right now, but it's just one question.
That's it.
But that's it. Are you working with plants? Because we actually do have one researcher who's doing stuff with plants, yeah.
That's all it takes is one, right? And then the race is on. And there's nothing worse if you have to start from scratch. So again, put in a little bit of forethought in designing something. Try and get as much mileage as you can. How much, is it flexible? Is it scalable? Is it sustainable?
And if you're doing software and can do drop-down menus, do as many drop-down menus as you can, because that will ensure the integrity of the data that you're collecting. Because every time you have a researcher write stuff in, you could have 5 researchers working with a salmonella strain that's all the same, and they will enter it in 16 different ways if they write it in, right?
And you know, biological agents don't, unlike chemicals, drugs, they don't have CAS numbers, where you can always go back to the CAS number and say, okay, well, it's got 15 synonyms, but I don't
Nor do about half of the chemicals that our researchers
Right.
work with have
Well, that's
CAS
true,
numbers.
Because they're unique and they just cook them up in the kitchen last.
So again, so if that's the case.
Or
if
they're a
that's part of your-
biological thing and don't have a CAS number to go with them.
So that's, you know, and that's an important feature that you may need to incorporate when you're designing something out. If you know you're gonna be faced with this is what's going on, don't ignore it, right? Lean into it. Figure out how to address it in a way that you can use it, rinse and repeat, rinse and repeat, rinse and repeat. Because you just don't have the time to keep designing something for every research project.
It's gonna depend on what the committee actually is. Is it IEC or is it combined, like hazardous chemical and radioactive materials and biological materials committee? We have separate committees.
Yeah, I mean, you might start out,
Institution, you might just have a research safety.
you might start out as the kitchen sink approach, right? Where it's one-stop shopping in one form that covers bio, rad, and chemical. Well, that might work fine for the first year or 2 years. And then one of those 3 elements grows beyond the capacity of the form, right? It morphs into its own program. So again, just, you know, the amount of time you spend up front thinking about these kinds of things can be really beneficial down the road. You know, you can reap the benefits 1,000 times over in time and effort. Any other questions? Okay, well, thank you. I hope you found this.